This video is about the Universal Semiotic Coding for Information Interchange, or USCII. Something I came up with is an alternative to ASCII. It's similar because it's a character encoding, but the difference is that instead of using random numbers like ASCII uses 65 to mean A, it tries to put a picture into the number. I got the idea from the arecibo-message, and if you're a geek like me, you have heard of the arecibo-message. They were trying to communicate a bitmap to aliens. Thing is that if you're just sending a bunch of on and off, there's no dimensions encoded in that. If you read about it here on Wikipedia, it breaks it down. There's no color in the message, but the color is used to tell you, oh, this is where they establish numbers, and this is where they establish our knowledge of physics and chemistry, and here's our planet, third from the sun, relative masses. But the part that I was interested in was the number of bits, because it's the product of two prime numbers, and it might hint a mathematically minded person into thinking, well, what if we chose those two numbers to use as a width and a height? So I thought, well, what if I started by trying to pick numbers using a font that had a prime width and a prime height? And the one that I found that seemed most suitable to start with was this 5x7 font. It has codes in the range of ASCII here, but it also has some holes that you see, which is where you have line feed or play a bell. I thought that I could draw pictures for those too. Now it's going to be pretty apparent that a USCII message is going to be larger than the corresponding ASCII message. A single character in ASCII fits in 7 bits, and one of these 5x7 bitmaps is going to need at least 35 bits. It's even longer than that, so let's try just the letter A and see what we get. And we get 125 bytes long, pretty large. Now we know that when you make even a 1 byte string in ASCII, it takes up more than that because you have to indicate where the string ends. But USCII is designed to call attention to this 35-bit pattern and potentially infinite noise around it. If you've ever looked into a memory browser, maybe a hex editor to view the bytes in a file, you realize it can be hard to tell what's code, what's data. And I wanted to just tear all that implicit knowledge out and make it clear as day. And I do that with these 5 solid blocks on the beginning and these 7 solid blocks on the end. And I call that the meter because it sets up the rhythm of these prime factors. Then we have our little A character from the PIC CPU font. But even that's not good enough. Imagine you're looking in memory and you see one of these abutting right up against another one. Then the 7 that ends one string might run up against the 5 that begins another, and suddenly there's 12 in here somewhere. So there has to be what I call the silence, dead space that leads and trails the signal. And I think it jumps off the page. You can even see it right here. And that's 7 40-bit blocks of 0 to open it, and 5 40-bit blocks of 1s to close it. No matter what is surrounding this in memory, you are going to be seeing these 5 solid blocks and these 7 solid blocks that set up that meter that I described. And there's also these 5 zeros that separate the character components. And you say, why 5? 2 reasons. One is that if I picked another number, like just 1 0, which is what I did initially, that introduces a whole new number in here, like why is there 1? And 5 is a number that we already want to reinforce. Also, when you take those 35 bits and you add 5 more bits to it, you get a multiple of 8. That means that USCII strings can be conveniently manipulated in the computers that we use today. So that's a fringe benefit. And you may not see that that's an A, but you can certainly see that that's the baby in this bathwater. So let's go look at it. Okay, we're going to just put a break here every 5 characters, or bits, represented as characters in this case. And you can see the A. To make it a little more obvious, I can just go ahead and replace all the zeros with a space. And there you see the A even more clearly. So let's go see the decoder, which accepts our hexadecimal input. And, you know, success, the ASCII conversion was 1 character long. the demo, as you can see, is very talky. It explains the pattern. So if you send this to your friends, it will help them decode it. But I'd really rather that you start without giving the decoder and see if they can figure it out, because I'd be very curious how many people can. I would assume most could. You know, the point is not that you're going to be ultimately drawing 5x7 bitmaps. So it could be a papyrus A triggered by this encoding. The fact is that when you can't decode it, the actual bitmap could be used to show you a representation of the missing character. This also works for the non-printable characters. Let's take line feed as a very popular one. So we'll put A and then a B on separate lines. And look, there's a picture of a down arrow. You know, kind of goes to the right and goes down. For all those gaps in the pick CPU table, I drew a picture. That gets encoded just like the characters do. Here's our A, there's our arrow, and there's our B. And similarly, the decoder can interpret that. So when we go to the decoder, it got it. Now, you've probably thought that 5x7 might be big enough to hold ASCII and perhaps drawings for the control codes, but there's no way you're going to fit all the Chinese characters. And that's true. USCII isn't just this one standard, it's a general strategy, and I actually found a 23x23 bitmap font for Chinese. It's commercial, but because it exists, it shows we could build USCII Unicode. I actually wrote a program that generates the files needed for the demo and the representations. I want to show you that because it uses some pretty interesting techniques. So let's go ahead and grab the repository for USCII off of GitHub. And we're done. It has a subdirectory called demo, and in demo you have the HTML and JavaScript and CSS for the demonstrations I've been showing you for encoding and decoding. But then there's also this other file, and that is a Rebel script which generates all the little images and the table for the JavaScript. Let's go ahead and grab Rebel Interpreter. And it's really nice because Rebel doesn't have installation dependencies really. It's only 0.5 MB, yet it has image magic type stuff built into it. It runs scripts off the network. It's very versatile. Let's save it as Rebel. And the one thing you do have to do is make it executable. So there you have it, and we'll run it. So it made an HTML table that I use in the specification on the website, and then it makes a JavaScript table which it uses programmatically to get the values, and it makes all of those little PNG files for the letters and symbols, and I'll show you how it does that. Now, if you're not familiar with Rebel the language, it's similar to Lisp in that it's code as data and data as code, the property known as homoiconicity. It's more readable. And every Rebel program starts with a header. Even if that header is empty, you still have to have that Rebel marker at the beginning. In this case, I'm, as usual, very verbose, and I use several of the different fields which are used by script categorizing libraries or the module system. So there's a lot of stuff that you can put into the header in addition to adding your own tags. But the first thing I get into with the actual code is the data to override the font. That could include any characters that I thought needed to be drawn better if they were in the font, or characters that just aren't in the font at all, like those first ones that we saw in the table. I start here with the null character and decided to make it just alternating bits. And for each of these, I've given them a rating. I think that's pretty good. How often are these used? Who knows? I mean, some of these you probably haven't really heard about unless you're very old school, like start of header, known as SOH. I was trying to build some kind of logic about using various inverse video symbols to say things. It got down to ones that are a little bit more reasonable, like end of transmission being a reverse video period, which seemed pretty good, and then, you know, inquiry looks trying to look like two arrows going back and forth. I don't know. At this resolution, it's hard to say. So I think the acknowledgement, ACK being a happy face, is pretty good. The bell being a picture of a bell, I don't know, maybe it should be a musical note. I don't know what's the most invariant way of representing that. But we get down through all those different symbols, and you can review these, and certainly feedback is welcome. Try to provide some of the rationale right there in line in the source so you can see what I was thinking, however crazy it might be. We'll go through all those, and then we get to the actual data from the PIC CPU, which is a Rebel binary. You can actually enter hexadecimal numbers as a binary string literal and then manipulate it on a per byte basis. So strings are Unicode code points, but these byte strings are actually bytes. So that's pretty cool. And then I got the functions to make a table in JavaScript or in HTML. And you can see this very literate way that HTML tags can appear in Rebel source. They're just like another type of string. It's one of the kind of very fascinating things about Rebel is how many different data types you have and subtypes. You can have a string type subcategorized as being a tag or as a URL, and it acts just like a string in terms of being able to get the characters out of it and modify it. But your code this dynamic language can be sensitive to and react to say, oh, I will do one thing for this tag parameter and another for this URL parameter, and it becomes a lot more expressive than when you're forced to do everything as a string. And down here you see me making the JavaScript table, just spitting out some strings and generating all the images. You can actually just say make image to create one, and then I'm just saying, convert 5 times scale and 7 times scale into a pair, which is another data type, which is just a 5x7, for instance, would be 5 by 7 as a pair literal. Now, if you've actually stuck with watching the video all the way up to here, you're my kind of people. Thank you very much. I'll make it only a little bit longer to tell you a little bit about the mindset I was in when I came up with this. I had been reading about the Rosetta project, which was this thing by the Long Now Foundation, who are also trying to build that clock that's going to last for 10,000 years. And they wanted to take a bunch of the knowledge that we have about the world's languages and etch them into a nickel disk. And they did the etching optically. It's not in any kind of data format. And if you go, you can browse what they put on the disk here online. So that project was on my mind when I was visiting the Mexican Museum of Anthropology. I was looking at the writing, actually. It wasn't necessarily this writing, but it was stuff that looked like this. And I was thinking about those Unicode characters, especially the really large ones where all you have is this big number coming from what's called the astral plane, if you haven't heard of that term. It made me wonder if it was possible to get the best of both worlds, basically, to have a digital format that could pull numbers and yet still have some sort of reduced picture in the number. Do I think this has practical value? It may. It's probably more a fun thing for people to read about, geek out over. Maybe computer science professors give a programming assignment to encode or decode. It's a fun programming problem. But also there are situations, a USCII character would be useful. It's very frustrating when you get those Unicode characters that come over and it just shows you a little number, like it's missing, but there's a number. There's no way on your system to even reason about what it might be. We can solve that problem. And there may be levels of bootstrap that you could use a USCII approach and then negotiate. So you start out with the pictures and then you move up to the numbers as a shorthand. Anyway, that's just a little bit more of my mindset. And I definitely would love people to get interested and join up in helping come up with the right drawings. It's not really set in stone. And one of the great things about USCII is if it fails and you can't stroke the character because it's changed, there's always that picture in there for you to look at and go, well, what was it? So USCII actually can survive changes better than many other systems could. Thank you so much for listening and viewing.